Welcome to the Explainer. You know, when a bank decides whether to give you a loan, that's not just a gut feeling, it's machine learning. So today, we're going to build our own kind of crystal ball. We're going to break down exactly how these incredibly powerful predictive models are tested to make sure they're not just accurate, but genuinely robust, especially when the stakes are sky high in the world of finance.
Okay, so think about it. In finance, these predictive models are literally the engine behind billion-dollar decisions. We're talking approving loans, trading stocks, managing massive amounts of risk, and they do it all in the blink of an eye. But what happens when one of them gets it wrong? I mean, a single mistake could spark a financial meltdown. So the real question we have to ask is, how do we actually build an AI that we can trust with that much money?
All right, let's dive into the core challenge, prediction in a risky world. Specifically, how we manage the uncertainty of credit risk. You know, this really is the biggest hurdle in lending. It all boils down to that one huge question: will this person pay back their loan? If you get it right, hey, you've got a profitable business. But if you get it wrong, you're looking at some serious losses. And that's exactly where predictive analytics comes in to be our crystal ball.
So at its heart, every loan is kind of a leap of faith, right? It's a prediction about someone's financial future. But here's the cool part. In this age of big data, we don't have to rely on just faith. We can use facts. By crunching thousands of data points, everything from credit history to how stable your income is, these predictive models can actually put a number on that risk. This helps lenders make way smarter and much safer decisions.
Okay, so how do we actually build this thing? Step one is all about laying the data foundation, getting our materials ready. And let me tell you, this is probably the most crucial step of all. Because in machine learning, there's a simple truth. Your model is only ever as good as the data you feed it. You've heard it before: garbage in, garbage out. So let's make sure we're building on solid ground.
And here is the absolute golden rule of all predictive modeling. It's simple, but it is totally non-negotiable. You never ever test your model on the same data you used to train it. Think about it. That's like giving a student the answers of the test right before they take it. To get a real sense of your model's power, you have to split your data into two separate piles, one for training it and a totally different one for testing it.
In this visual here, it shows you exactly what I mean. See the unshaded part? That's our training data. That's the history book our model gets to study and learn from. Then you have the shaded area. That's our test data. It's like a sneak peek into a future the model has no idea about. By testing it on this data it's never seen, we can be confident it's not just memorizing old answers, but that it's actually learned the patterns it needs to predict what's coming next.
All right, our data is prepped. So on to step 2, building the predictive engine. This is really about choosing the right tool for the job. And honestly, it's a lot like picking an engine for a car. There's a whole range of them out there, and each one has its own strengths and weaknesses. Let's look at a couple of the more common ones.
So for example, on the left, you've got something called logistic regression. This is like the workhorse for classification. It's perfect for answering simple yes or no questions, like, is this customer going to default on their loan? But then on the right, you have a totally different beast, an ARIMA model. This is built for time series forecasting, predicting future values based on what's happened in the past. Think of it like a really sophisticated trend spotter, perfect for trying to predict where stock prices or the housing market might go.
Okay, step 3 is where things get really interesting. Testing the model's mettle. We're putting its predictions right under the microscope. So our model is built, but it is nowhere near ready for the real world. Nope. Now comes the moment of truth, the actual test. We're going to take that test data, the stuff it's never seen before, and we're going to throw it at the model to see how it holds up under pressure. This is really where we find out if we built a true predictor or just a pretender.
And our first tool for this test is called the confusion matrix. Now, don't let the name fool you, okay? It sounds complicated, but it's actually a super straightforward tool. Just think of it like a simple scorecard. It just breaks down all of our model's predictions into 4 basic buckets, so we get a really clear picture of what it got right and, more importantly, what it got wrong.
So look at this table. It lays it all out. The true positives and true negatives. Those are our wins. That's the model getting it right. But the errors, that's where the story gets really interesting. A false positive. That means we predicted someone would default, but they actually would have paid it back. So we denied a loan we shouldn't have? That's a lost business opportunity. But the false negative? Oof, that's even worse. That's when we gave a loan to someone who ended up defaulting. That's a direct financial loss. The whole game here is to build a model that gets us as many wins as possible while keeping these costly errors to an absolute minimum.
So the confusion matrix gives us the raw numbers, which is a great start, but it doesn't quite tell the whole story. The bigger question is, just how good is our model at telling the difference between the two groups, between the defaulters and the non-defaulters? We need a way to measure its overall power to do that, and that's where our next tool comes into play.
And this is it, the ROC curve. It's a really powerful way to see a model's performance at a glance. So that blue line, that's our model. And the dotted line, that's just random guessing, like flipping a coin. So the goal is for our blue line to get as far away from that dotted line as possible, bowing up and to the left. The more it bows, the better our model is at separating the good risks from the bad ones. That number you see, the area under the curve, or AUC, a score of 0.87 is really, really good. It tells us our model is a much, much better predictor than just random chance.
Okay, so we've established our model as a statistical success. That's great. But let's be real, in the business world, statistics don't pay the bills. The real question is, what's the actual business value here? What's the ROI? The ROC curve told us it's accurate, but now we need to know how much more efficient does this make us? This is where we get down to brass tacks. And this, the gains chart, is all about that efficiency. It shows us exactly how much better our model is at sniffing out high-risk customers compared to just picking them randomly. Now check this out. In this example, if we only focus on the top 50% of customers that our model flags, we find 90% of all the people who actually default. I mean, that is a massive improvement in efficiency. It lets us point our risk management efforts exactly where they're needed most, instead of wasting time and resources. Right then, step 4, creating a truly robust system. Because as you'll see, a single model just isn't enough. So we've got this great model, right? It's accurate, it's efficient, it's ready to be deployed, yeah? Well, not so fast. A great model is just one piece of a much larger puzzle. To build a system that's truly robust, one you can rely on day in and day out, you have to think way beyond just the algorithm. You need a system that can handle a world that is always changing.
And hey, this isn't just me saying this. This is serious business. Regulators, as this quote shows, are all over it. They are demanding that financial institutions have these sound practices for model risk management locked down. So what that really means is that building a great algorithm is only half the battle. The other half is building the entire system around it to make sure it's being used responsibly and effectively, day after day.
So what does one of these robust frameworks actually look like? Well, it pretty much boils down to these 4 key pillars. First up, you need clear policies. Everyone needs to know the rules of the game. Second, you need quality control, which means having independent people check to make sure everyone's actually following those rules. Third, regular audits. This is about actively looking for any potential weak spots before they become big problems. And finally, and this is so important, continuous monitoring. Because a model that was a genius yesterday could be completely wrong tomorrow if market conditions change. You have to keep watching it.
And all of this leaves us with a really big final question. As these AI systems get more and more powerful and more complex, who is responsible for testing the tests? Who watches the watchers? See, it's not just about building a crystal ball anymore. It's about building one that we can actually trust. So what do you think? As we move forward, how do we make absolutely sure that the predictive systems shaping our world aren't just powerful, but that they're also fair, robust, and reliable? It's something we all need to think about. Thanks for watching.